Today's lesson is going to look at the percentage composition of compounds. When we talk about the percentage composition of a compound, we are talking about it in terms of its mass, not by the numbers of atoms. So if we think of a chemical like magnesium oxide, and if I said to you, what's the percentage composition of magnesium oxide? Some people might say 50% magnesium, 50% oxygen. And this would be true if we were talking about it in terms of numbers of atoms per compound or per molecular formula. But when we talk about the percentage composition, it should be understood that we are referring to the mass of it. And when we talk about the mass, we need to be aware of the molar masses of our compounds and each element within. And then that drastically changes the breakdown of the percentage of each element in the compound. So an example is the percentage composition of water, which we know is H2O. And by now we should remember that oxygen weighs 16 grams per mole, hydrogen weighs 1.01, although there are two of them. So the percentage by mass is higher for oxygen than it is for hydrogen, given the molar masses of each of those elements. You calculate percent composition or percentage values in various other areas of your life. So I want you to stop the video right now and work through the example on your note that deals with ingredients in a recipe. When we calculate the percentage composition of a compound, we use this basic formula. We take the total mass of each element in the compound and we divide it by the total mass of the compound. And depending on how many elements are in your compound, you will have either 2 percentage values or 3 or 4. It all depends on the formula of your compound. The masses that you can use can be actual masses, so experimental values that you obtain in the lab, or they can be theoretical. And a theoretical mass refers to the molar masses that we find on the periodic table. Let's try an example of using our percentage composition formula in a chemistry application. So it says here, a chemist took a 125 gram sample of water and separated it into 13.5 grams of hydrogen and 111.5 grams of oxygen. What is the experimental percent composition? So this is telling me when I see experimental that I'm using data that was obtained in a lab setting. So I have 2 elements. I'm going to need to do 2 calculations. We always want to see the calculation, but in a case like this, if you just put the basic calculation down and then just sub in per element, we are fine with that. So we need the mass of the element, and we're going to divide by the mass of the compound, and we're going to multiply by 100%. So let's set it up for hydrogen first, and just substitute your values in. So we're dealing with 13.5 grams of hydrogen. The mass of the compound of the water is 125 grams. We're going to multiply by 100%. We are aware of significant figures. We're dividing, so we need the fewest amount, which is 3, and we get a percentage value of 10.8%. We're going to do the same thing for oxygen, and we're going to sub in those values. So there's a little bit more oxygen, 111.5 grams. We divide by 125. That doesn't change. We multiply by 100%, and we round to sig figs, which is 3 from the total mass of the compound, and we get a percentage value of 89.2. And you should notice that these percentage values equal 100. Okay, if done properly, all of your percentage values should add up to 100%. When we're not given lab data, we can still calculate the percentage by mass using theoretical values. So here's the same kind of question, talking about the breakdown for hydrogen and oxygen and water, but they don't give us any data. So when we know, we've been asked to solve for the percent by mass, and they don't give us anything, we're going to use molar masses. So we're still going to set up the base formula, so percent composition. And now, instead of saying mass of my element, I know I need to use the molar mass. So I'm going to just write that in, symbol in for molar mass instead. So molar mass of the element divided by molar mass of the compound. There's a direct relationship between molar masses and actual masses. And then we're going to multiply by 100. You don't need to rewrite this every time. Now we're going to sub in for each element. So hydrogen's molar mass is 1.01, but there's 2 hydrogens. We have to account for that. So we're going to write 2 times 1.01 grams per mole. And then we're going to divide by the molar mass of water, which is 18.02 grams per mole. And again, all of you know how to calculate that at this point. We're going to calculate the value, and we're going to round to significant figures. Now here we are not using measured data. So we have our constant molar masses, but it's all we have. So we still have to use them. And because 101 has only 3 significant figures, we're going to round our answer to 11.2%. We're going to do the same thing for oxygen. So oxygen just has 1 atom. So it's just a 16 gram per mole divided by the total molar mass, which is 1802 grams per mole, multiplied by 100. And we're going to round now to 4 sig figs. That's what we see in our molar mass data. And we get 88.79%. So our values are slightly off of the question before that was using actual lab data, but that's okay because we know with lab data, there's always some errors built into our calculations and the values that we obtain. We'll have you try to get these percent composition values for glucose. So I give you the chemical formula there for glucose. You're going to use, if we don't give you any data, you have to use molar masses off the periodic table. Be aware of the number of atoms of each element and try to get these answers that are on the slide sheet. This last example is a nice application of percent composition to actual masses of compounds. So it wants us to calculate how many grams of phosphorus are in a 175 gram sample of sodium phosphate. So we know that sodium phosphate would have the formula Na3PO4. We know that the total mass is 175 grams. We just want to know how much phosphorus or what is the mass of phosphorus within that 175 gram sample. And we can calculate that if we know the percentage that phosphorus makes up in that compound through its mass. So the first thing that we're going to do is we're going to come up with the molar mass of sodium phosphate. We have to use these theoretical values because they don't give us anything actual besides the total mass of the sample. So when we add up our molar masses for 3 sodiums, 1 phosphorus, 4 oxygens, we get a value of 163.94 grams per mole. So let's calculate the percentage of phosphorus in this sample. And we could calculate the percentage of sodium or oxygen, but they're not asking us about that. So they just want to know how many grams of phosphorus are in the sample. So we're going to take the molar mass of phosphorus, and we're going to divide by that molar mass of sodium phosphate and times it by 100%. So a phosphorus weighs 30.97 grams per mole. There's only 1 atom of it, so I don't need to alter that value. And we already calculated this molar mass of sodium phosphate at 163.94 grams per mole. We divide that out, multiply by 100, I get a percentage value of 18.89%. So call it 20%. So roughly 20% of the 175 gram sample is phosphorus. So let's calculate the amount of phosphorus that makes up that sample. So we're going to take 175 grams. There's no real formula that we're going to use here. And we're going to multiply by 18.89% But remember with percentage values, when you use them mathematically, you have to divide by 100. You have to put those percentage values into a decimal form. So once we do that, then we multiply it by 175 grams. We get a total of 33.1 grams of phosphorus in that sample. And again, keep track of significant figures all the way through. We need 3 sig figs here due to the sample or the mass of the overall sample.